In this section, we're going to be looking at one-way analysis of variance. And for analysis of variance, basically you're testing the hypothesis, the null hypothesis, that 3 or more population means are equal. So you have to have at least 3 here, and you could go up to an n number of population means are equal. The alternative hypothesis for the null hypothesis is at least one of the means is different from the others. Now it doesn't say which mean, it doesn't say the third mean or the fourth mean, it just says at least one of the means is different than the others. So it could be 1 mean is different, 2 means, etc., but it doesn't identify exactly what mean that is. Now in order to perform this test, there are some requirements that must be met. And for your My Math Lab homework, usually we just assume that those requirements are met. So it's nothing that you have to check particularly for this, we just are usually assuming that those assumptions are true. The first requirement that must be met is not very surprising. Basically it says the populations have distribution that are approximately normal. So the samples come from normal populations. And they don't have to be exactly normal, they can be approximately normal. The second criteria is that the populations have the same standard deviation. Now, by the same, they don't mean identical, they mean very, very close. So not the samples here, but the populations. Have the same standard deviation. And of course, sigma is our population standard deviation. If this is not met, if this criteria isn't met, there's other tests that we can use. And the same for the first criteria of the normal distribution. If that criteria is not met, there's other processes that we can use to test this hypothesis. The third criteria, that this comes from a simple random sample. And the fourth criteria is that the samples are independent of each other. And the last criteria that we have here is the different samples are from populations that are categorized in only one way. Now that last criteria sounds a little bit strange, but when we talk about the different criteria that must be met, what we're really getting after here is a category like small, medium, or large. So it's only categorized in exactly one way. Now when we're talking about these types of problems, again, we assume, and when we're working in My Math Lab, they'll usually show us that these criteria have already been met. So we usually don't need to actually go through and check for those, but it's always a good thing to look at. So again, this last criteria, the samples are from populations categorized according to a single factor of, let's say, size, small, medium, or large, for an example. Now, if all these requirements have been met, basically our test statistic that we're going to be using follows an F distribution. Now the shape of the F distribution can change quite a bit based on the degrees of freedom. Now there's a couple different ways we can calculate this, but mostly we're going to be relying on our calculators quite a bit to calculate our test statistic and our p-value here. The F distribution is typically considered a right tail skew or skewed to the right. So our F distribution will have some sort of a critical value, and we'll be using the p-value approach mostly, but we'll have some sort of a critical value, It's a right tail test, so anything beyond the critical value is when we reject HO. And then of course anything not beyond the critical value we'd fail to reject HO. And then what we do is we just take our test statistic and we compare it. If our test statistic lies between 0 because the F distribution is always positive and our critical value, then I'd fail to reject. Anything beyond the critical value we would reject HO. So that's the F distribution that we're going to be using. We don't have tables because there's several pages of tables for the F distribution, so again we rely on our calculators for those. So let's go ahead and look at steps in analysis of variance. Now we usually abbreviate analysis of variance with ANOVA. So you'll usually see the words ANOVA. So as usual, our first step is to state HO and HA. And again, all the means, all the population means are equal. And we can have as many means here as we needed. The alternative hypothesis is at least one of the means differs. Now remember, it doesn't say which of the means, it just says one is different. Same second step as usual, state the level of significance. The level of significance is usually given to you in the problem. And again, that's equal to alpha. Step 3 is to calculate our test statistic. And again, that's going to be given to us in our summary values. Step 4, we're going to calculate the p-value. And we will either be using our calculators or we'll be given the output from some statistical software to help us calculate the p-value. Step 5 is we make a decision. And this is nice because it's the same thing that we've always done. If my p-value is less than or equal to alpha, my significance level, I'll reject HO. And if my p-value is greater than alpha, I'll fail to reject HO. So this is the same. Step 6, you'll summarize. And you'll either say that the data supported the null hypothesis, that all the means were equal, or you'll say the data supported the alternative hypothesis, that at least one of the means was different. So that's kind of a quick rundown of the steps, and those are very familiar because we've been using these steps over and over again. So I think the next thing we'll do is to go ahead and work a problem. So for this problem, we have a sample of colored candies, something like Skittles or M&Ms. So a sample of colored candies was obtained to determine the weights of different colors. The analysis of variance table is shown below, and so this is output from some statistical software. It is known that the population distributions are approximately normal and the variances do not differ greatly. So that's telling me that the requirements of the test have been met. We want a 5% significance level, so that's our alpha, to test that the mean weights of the different colored candies is the same. And then we have a part 2 here that we'll answer toward the end. So for our output that we see here, really the only thing that ends up mattering to me is the test statistic. So again, this is the test statistic, and this is the p-value. Now if I wanted to use the critical value, I could, but really the p-value and the test statistic will work great. So let's go ahead and run through the steps of our test. So again, 1, state HO and HA. Now what they don't show us here or tell us is how many different color candies that we have. Now they don't come right out and say it, but our different colored candies can probably be found right here in the degrees of freedom. But it's not 8. It's going to, of course, be affected by n-1 and things like that. So I don't really want to focus in on that so much. I just want to say all of the colors have the same mean or average weight. And then the alternative hypothesis would be at least one of the means is different, or at least one of the averages is different. Okay, so that's my first step. Second step is to state my level of significance. And of course, that's alpha equals 0.05. And again, that's given to us right here in our problem. Now, step 3 is our test statistic, and you really need to label these. You don't want to just throw a number down. You want to label what the number is. And our test statistic is an F value, and we can see that it's 2.5515 from the output. Next is our p-value. Now our p-value is also given at 0.015. Now we can calculate the p-value based on the test statistic. We don't actually use that, but that is what we use to find the test statistic, so we still list it. Now we make a decision, and in order to make a decision I need two pieces of information. I have p equals 0.015, and I have alpha equals 0.05. Well, if we compare these, we can see that p is less than or equal to alpha, therefore we will reject HO. Okay, so that's our decision, is to reject HO. Now, if you think about the null hypothesis said that all the means were equal. So the alternative hypothesis would be the one that has support here because we rejected the null. So what I have here then is I have support that at least one of the means is different. So if we go back to what the original question one, it says if the candy maker wants the different color populations to have the same mean weight, do these results suggest that the company has a problem requiring corrective action? So I guess that's going to kind of come up with the summary as well. So let's write our summary and then answer that question. So for here, the summary would be able to look at something like, there is sufficient evidence So we do have sufficient evidence to talk about rejecting HO in favor of HA. So there is sufficient evidence to warrant rejection of the claim. Now remember, we're rejecting HO, and so basically what that claim was that the colored candies have the same average weight. And that's of course for each color. Now remember, the company's purpose was to say something that the candies, regardless of color, had the same weight. Well, we can see for this particular case, does the company have a problem requiring corrective action? And it seems like they probably do. So does the company have a problem requiring corrective action? Now the only reason that they need to have corrective action is that they are claiming that all of the different colors have the same average weight. Okay, so that's why they have to have corrective action. So as we work here, we'd have to say yes, because it is likely that the candies do not have equal mean weights. And then so they'd have to go back through their manufacturing process and figure out how to fix that if it was important enough. So this is an example where you're given the output, where you're not actually asked to calculate anything. You're just asked to make a decision basically because you're given the values of P and alpha. But you do need to go through the steps of hypothesis testing, and that's a very important habit to get into. The next example, we're going to be given raw data, and then based on the raw data, we'll use our calculators to come up with a test statistic and the p-value. Okay, for this last example, we have the data was obtained from a car crash experiments. The table values that we see below are the chest deceleration data for the dummy in the driver's seat. We want to use a 5% level of significance to test the null hypothesis that the different weight categories have the same mean. And then at the end we want to say, do the data suggest that larger cars are safer? Now we can't determine the answer to this question from the analysis of variance. We're going to have to do some informal procedures to figure out the answer to that question if needed. So I have 4 different types of car. I have subcompact, compact, midsize, and full size. And if you notice, I took 5 observations for each type of car. So our sample sizes are the same. If our sample sizes were different, we'd have a different procedure to use. So it's important that we note that sample sizes are the same. We'll assume that the underlying distribution of scores or deceleration for each of the dummies in the driver's seat is the normal distribution. We'll assume the standard deviations are about the same and all the other requirements are met. Now, in order to work this problem, we need to use our calculators to input the data. So what we're going to do is we're going to go to second stat, and then we want to clear out our lists. So let's try that again. Not second stat, just stat. Sorry about that. Edit, and then of course go ahead and clear out your lists. And we're going to enter subcompact in our first column, compact, midsize, and full size. So we're going from small car to large car, small number in our list to large number in our list, L1 to L4. Okay, so for subcompact, which I'm putting in L1, I have 56, and I'm entering across 56, 51, 57, 51, and 54. Now I'm guessing that when you enter these, you're not going to have the 0.000. I'm not sure why my calculator is doing that this time, but you probably won't have that, and that's fine. And again, I'm listing compact now across 48, 54, 55, 53, 45. And then L3 would be our mid-size car. So it would be this third row. It would be 50, 48, 45, and 52. And then L4 would be our last row, 49, 50, 49, 45, 40. So even though our data is originally listed in rows, when we input it here, we have it in columns. Okay, so once that is done, we go ahead and go to Stat, Tests, and we're looking for the ANOVA test. And here it is on mine, it's on the very bottom, ANOVA. And basically what I need to do here now is I need to list the L1, L2, L3, and L4 that I want to use. So I'll go second L1, comma, second L2, comma, second L3, comma, and second L4, and close parenthesis. Now before I actually hit enter here, I'm going to screenshot this and put it into our lecture so we can see that these are the steps that we need to take. Now again, I haven't written anything out yet in terms of my hypothesis test. This is just getting us started on how we're entering our data. Let's go ahead and go back to our calculator and hit enter. And this is all of our output. Now if you notice the arrow at the bottom, we have more information if we scroll down. And these are all the different, this is the standard deviation within, the sum of the squares, the mean squares. A lot of this is information that we really don't use. The information that we'll want is up here with our test statistic and our p-value. That's the most important thing for us. So let's go ahead and screenshot our output. And again, there's more listed below, but we won't be using it. And then we can work our hypothesis test from here. So this is our calculator input. And then from here we get our test statistic. And then our second value here is our p-value. Now all the other information we're not really going to use. So let's go ahead and get started. So first step in hypothesis testing for analysis of variance is to state HO and HA. So for here, what we're saying is the average deceleration of the test dummy driver is going to be the same for all the different types of cars. So if we wanted to, we could write this population distribution a little bit different, or sorry, this population hypothesis a little bit different. We could say the mean for the subcompact is the same as the mean for the compact, is the same for the mean for the midsize, is the same for the mean for the full size. So, or I could just write this out in words. The average for each of the car categories is equal. And of course our alternative hypothesis would be at least one of the means is different. Now one thing that we could look at that would be pretty interesting, we should be able to pull this up on our calculator as well, we could look at the mean for each category. So we already have the data that we need. Let's go to Stat, Calc, one variable statistics. And we could look at second L1 and calculate that. And we can see the mean for L1 is 53.8. So we can see over here that our sample size is 53, or sorry, our sample size is 5, but my average for that sample is 53.8. Then we could go in and do the same thing for L2, one variable statistics. So for our second group, the average is 51.0. So it looks like these are pretty close to each other. Not too far off. Let's check midsize next. This would be Stat, Calc, one variable statistics, and that's just L3 this time. And we can see I have 48.2 for my mid-size option. Oops, I already forgot what it was. 48.2 for my mid-size option. So that's pretty similar as well. That doesn't look like there's anything that's too different. And let's check our full size last. Stat, Calc, one variable statistics. And we go to second L4. And this one is 46.6 for my last one. Now this one is a little bit different. So this goes clear up from 53.8 clear down to 46.6. So that's a difference of, let's say, about 7.2. And I don't know if that's a big enough difference for this to reject HO that they're similar or not. We'll have to run through the test to see that. But it looks like there could be a little bit of a difference. So again, we're checking to see if the average deceleration is the same for all of our categories here. So the second step is to state our level of significance, which I believe in this case was 0.05. That's pretty a common one to use. 3 is our test statistic. We get our test statistic from right here, 3.894. Now the test statistic is used to calculate our p-value, and that's done automatically for us on the calculator. So for our p-value here, I get 0.029. And then we make some sort of a decision. Now to make our decision, I need to know my p-value is 0.029, and I need to know my level of significance is 0.05. So I can see by comparing these that p is less than or equal to alpha, therefore we're going to reject HO. Of course, our last step is our summary. So for our summary here, what we're really getting after is that it appears that the averages are different. So again, just to back up, our p-value was 0.029. Our p-value was less than our level of significance, so I would reject HO. So for our summary, we have the null hypothesis is rejected. So I can say in this particular case, and we can scroll up here for an example, there is sufficient evidence to warrant rejection. So there is sufficient evidence to warrant rejection. Of the claim that the average deceleration for all car types is the same. So that means at least one of these has a different average deceleration. Now again, this doesn't say which one is different, it just says that one is different. At least one is different. There could be two that are different. So if we go back up to our problem, we have this question, do the data suggest that larger cars are safer? So this information that we have so far doesn't answer that. So let's try and answer that out another way. So do the data suggest that larger cars are safer? Well, one thing that we would need to know for sure is if smaller deceleration equals safer. And it looks like to me, if we run back up here and have a look, larger cars have a smaller deceleration. So that must mean what that is. Larger cars have the smaller deceleration. So the implication here is that smaller or lower deceleration implies that that car is safer. Well, it kind of looks like the larger cars are safer then, but one informal thing that we could do, there's formal tests for this as well, but one quick informal thing that we could do is we could go to second stat plot, and we could go to plot 1, and what we could look at here then are trying to figure out our box plot. So if you click across, we want to make sure this is turned on. If we click across to our box plot, it's kind of hard to see on the screen here. This one shows our box plot with outliers. This one shows without outliers. Oops, let me go try and grab that again. Our lists will change there. It won't ask us for two lists when we get to our box plot. Okay. Our X list is L1. Our frequency list we don't have, and I can put this one in blue, we'll say. Then I can go to second stat plot again, and I can turn my second plots on. I'm going to do the same thing. I'm going to go to L2, frequency is just 1, and then I'm going to go to second stat plot again, and I see a mistake here on this plot 1, so let me go find that. X list is L1 frequency. There is not a frequency list. Okay, so let's see if that will stick. Oh, it went back to L2. I must need to put in the number 1 like we have there. So second stat plot. Let's go try that again. There we are, 1. Second stat plot, and it looks like it's stuck this time. We're going to go to plot 3 and turn that one on. Then we'll do the same for plot 3. Go down and choose the same box plot, the one without outliers. And here we want to go to L3, so that's second L3. Frequency is 1, so that looks good. Second stat plot, and we want to go to our fourth. It's a good thing we don't have more than 4 types of car here. Whoops. So second stat plot. Oh, maybe we can only do, yeah, I guess we can only do 3 box plots. Well, let's go ahead and check these, and then we'll throw out one that's different, and then we'll throw back in the 4th stat plot, or for the 4th type of car. So let's go ahead and hit graph, and of course we might have to do the stat zoom. We'll see here in a second. Let's go zoom. Zoom stat is number 9 for me. It might be a different number for you. And this shows the 3. So this was my subcompact. This is my compact. This is my midsize. So I think what I'm going to do is I'm going to change this so it goes compact, midsize, full size. So I'm going to change the order here since I can only fit 3 on my screen, because I've already seen what L1 is doing. So I'm going to change this to L2. L3 and L4. It just gives me a chance to see them in the same order, but I can fit them all on the screen now. And then, sorry, second stat plot. And then let's go to L4 for our last one. We haven't seen this one yet. Okay, let's go ahead and hit graph again. They should show up this time. So this would be, L1 would be up here somewhere. L2, which was compact, mid-size, and full size. So if we could see that first one up on the screen, I don't think it would overlap with this one down here. So let's go ahead and do zoom stat again, see if we can see the bottom end of that 1 box plot. Here we are. So you can see that it does look like it's lower probably than this first one that we had to get rid of. So it does look like this large size or full size car does have definitely the lowest deceleration. So do the data suggest that the larger cars are safer? Yes. Well, first of all, because we rejected the null hypothesis, and then when we look at the histograms, or sorry, the box plots, the data suggests that the mean deceleration for larger cars is smaller. So I want to look at one other thing. I'm going to go to second stat plot, and I'm going to replace this one with L1 since that was our largest values for deceleration. And again, the only reason I'm having to switch these around is we don't have the option of 4 box plots on the same screen. Otherwise I could see them all. So let's go ahead and go to zoom. Zoom stat, just to make sure I can see everything. And here's my output. And I can definitely see that there is no overlap between the top and the bottom case here. So if you recall, this was L1. So this is subcompact. Now L2 we skipped, that was compact. This one is midsize. And this one is our full-size car. So because we couldn't fit 4 box plots on the screen, we skipped compact. Compact car. Now this isn't a formal test, but just informally I can see that the entire range of full-size values does not overlap with the subcompact at all. So that's why I'm showing, or that's why I'm thinking that the data suggests that the mean deceleration for larger cars is smaller. So do the data suggest that the larger cars are safer? I would say yes. First of all, we rejected HO. So we rejected that the means or averages are equal, so that means at least one is different. And if we look at the box plot and the data suggest that the average or mean deceleration for larger cars is smaller. And because that deceleration is smaller, meaning the value is smaller, not the car is smaller, but the deceleration is smaller, meaning the car is safer. Okay, so you have to be careful about the smaller and meaning the deceleration and not the size of the car there. So we're really relying heavily on the calculator to do a lot of the computations for us here. We're just more focusing on the output and also the analysis of the information that's provided. As usual, if you have any questions, please bring them to class, stop by my office, or you're always welcome at the Math Center as well. Good luck.